Welcome to Chapter 11, Vibrations and Waves. This is our last section of Section 1, and we're going to talk about something called a simple pendulum. What we'll be doing this time is we're going to explain how force, velocity, and acceleration change as an object vibrates with simple harmonic motion. A simple pendulum is a way that we can model the motion of things like these trapeze acrobats, or really anything that swings, like a child on a swing, and anything else that swings. And we're going to use this simple pendulum model to model this. There are several parts to a simple pendulum model, and it will always have these three parts. It will have a bob, okay? So this here, this mass on the end, this is what we call the bob. Okay. We also have the string, which is a little bit obvious, but the trick here is we pretend it has no mass because it makes things more simple, and this is a simple pendulum. And the last thing we need to remember is that we're going to always ignore friction and air resistance. For the same reason, there's no damping if there's no friction or air resistance, and it makes the whole model easier to calculate and understand. So the first thing we have to look at is we need to find out, does a simple pendulum have simple harmonic motion? And the answer is that it sometimes has simple harmonic motion. So what we need to do is remember the rules of what makes something have motion. So when we look at this, remember the key is that we need to have a restoring force, and that needs to be proportional to the distance from equilibrium. So on a pendulum, equilibrium is essentially the point at the bottom point of a swing. So it can swing up here and swing up here, but this point in the center here is our equilibrium position. So what happens is we end up with this force of gravity, okay? And any time that the pendulum isn't at the equilibrium position, the force of gravity is not opposite the string pulling it up. So this Ft stands for the F of tension of the string, and just the force pulling the bob up. So anytime it's swinging higher than the equilibrium position, what you end up with is end up with part of the force of gravity is opposite the string, and part of it will be going towards the direction of the equilibrium position. So this here, this force of gravity in that direction is our restoring force. And it turns out that as long as the angles that we're working with are less than 15 degrees, okay, this is very key for you to remember. As long as that angle is less than 15 degrees, it is simple harmonic motion. If it's more than 15 degrees, however, then this force of gravity stops being proportional to the distance from equilibrium, and it's no longer simple harmonic motion. So this is the key here. It is simple harmonic motion when the angle here, this angle, is less than 15 degrees. So simple pendulums are really a great way for us to model complex systems. We use simple harmonic motion to do that because our pendulum can act like simple harmonic motion for angles less than 15 degrees. And assuming no friction, it means that with our simple pendulum, we will have conservation of mechanical energy. And this is one of the things that really makes this a useful tool. So let's look at an example here. We talked about this a little bit before, but I want to go into it in more depth. So this is a graph that you can find it in your book. And remember, total mechanical energy is constant when there's no friction. Okay, so here I'm just going to put a reminder, no friction. Okay. So what happens then while the pendulum swings is if we start it up here, again, as long as this angle is less than 15 degrees, this one here, okay, we end up with all potential energy here because this is essentially the highest point. So we have potential energy, right? And then it's going to swing down. At this point, all of that energy, this is the bottom of the swing, it can't get any lower, so it's all kinetic energy now. And then it's going to keep swinging back up converting all of that back into potential energy. Then the process will reverse, and it will keep going on and on and on until we stop it, or in the real world, friction would stop it. So that's what this graph is showing us here. If we look at this graph up here, we've got the total mechanical energy. All of it is potential energy to begin with. The potential energy decreases at the same time the kinetic energy increases until it's all kinetic here at the bottom and zero potential. Then it's converted back onto potential energy until you hit the opposite side where it's the top of the swing. And there's no kinetic energy at that point when it stops before changing directions. So let's look and compare this now to our box on a spring, because we've decided now that both are simple harmonic motion. And now that we know they're both simple harmonic motion, I just want to point out something kind of interesting. Okay, so here we have our pendulum, right? And the pendulum starts here, it swings, it hits the equilibrium position, it keeps swinging up higher, swings back, keeps going back and forth, okay? So as we do this, if we look here, I already wrote that if I have time going in this direction, we could draw a graph of its position, and if we did that, we end up with something that is going to look kind of like this, okay? And we do the same thing over here. Now we've got our box on our spring, okay? It's going to come through, go over, and come back, okay? Now if we showed this repeating over and over and over again, because this is periodic motion and it's also simple harmonic, we would find that you just end up with a graph that looks like this, and it will keep repeating. And my graph isn't perfect, but you get the idea. We get this graph that goes back and forth. This is going to end up to be important later. So I just want you to start getting that idea in your mind that we can graph what happens over time, and we get this repeating motion. So now this is the full graphic from your textbook, and I just want to talk a little bit about the forces, the acceleration, and the velocity. So if you notice, what this graph is showing you is it's showing us that when the pendulum or the box is the furthest point away from equilibrium, we end up with a maximum force, or if storing force is the biggest. And because of that, remember F equals ma, if you remember from chapter 4. And since F equals ma, our acceleration will also be a maximum. When it's at this point, it's actually stopping and changing direction, so the velocity is 0. Okay, then it moves through to the equilibrium position here. And you can see then that the velocity will be the maximum, right? But our force and acceleration becomes 0. Okay, that's because at this point there's no restoring force. The spring is neutral, the pendulum's at the bottom of the swing. I will also want you to notice at this point that, remember, we just talked about how this one is all PE, the maximum displacement, and in equilibrium it's all KE. Remember, kinetic energy has to do with motion, which is why we get, if we have maximum kinetic energy, we have maximum velocity. Okay. Then it converts it all back into potential energy. We go back to a maximum force and a maximum acceleration. Through equilibrium, it's all kinetic energy. These become 0 again, velocity is a max, and then it cycles back to where we started with all potential energy, no velocity, and a maximum force and acceleration. So this is a repeating process. Remember, in the middle, we'll have a little bit of velocity and a little bit of acceleration and force, but on the ends, it's all force and acceleration, and in the middle, it's all velocity. That is the key part to this. Go ahead and let me know if you have any questions in class, and I will see you guys there.